Hello, this is Dr. Neff, and this video is about intermolecular forces. As this figure shows here, intermolecular forces are the forces of attraction between neighboring molecules in a collection. This is different from bonds, which are intramolecular forces, and those are the attractive forces within a molecule. So this figure shows, for example, the bond between the hydrogen and the chlorine in HCl, and the IMF between the neighboring HCl's. And so that's what we're going to talk about today, is the IMFs. So intermolecular forces are one of the most important topics, I think, that you learn in chemistry. And they're certainly one of the most applicable concepts and something that you can apply to all kinds of things in your everyday life. The strength of the intermolecular forces in a substance is what determines the natural state of that substance. So if you have really weak IMFs, your substance is going to exist as a gas. If they're slightly stronger, your substance will be a liquid. And if they're very strong, the substance will exist as a solid. And so this also affects important properties like melting point, boiling point, solubility, which is whether something will dissolve in something else, and in general, how a molecule interacts with other molecules. We're going to start by talking about dispersion forces. These are also known as London dispersion forces. Oops. But we'll just call them dispersion forces. And these are the only type of intermolecular force that nonpolar molecules have, but all molecules have these, whether they're polar or not. And so this type of IMF results from an electrostatic attraction or interaction between induced dipoles. So I need to explain what we mean by induced dipoles. Okay, so this slide shows step by step how a dipole is induced, or what we mean by the induction of a dipole. So this is showing two atoms that are identical, and if you look at the subatomic view, since each of the atoms has 2 electrons, these are helium. And the top view shows the polarization view, so it's just showing the electron cloud. And since they're both helium, when they're next to each other or just when they're by themselves, you can think of the electron cloud as being evenly distributed around the nucleus. And that's shown both as the polarization view and the subatomic view. But there's nothing that says that those electrons aren't moving and that they're always evenly distributed like that around the nucleus. So that's what the second view is showing us. That's showing that how at any one time the electron density can be polarized. What I'm drawing to your attention here in the second picture of atom B. The electrons in atom B have moved over to one side of the nucleus, so they've become polarized. What that does now is it affects the electrons in the next atom. So these electrons are going to repel those electrons. And how we show that in the big view is that since there's more electron density on this side, we show that that side of the molecule or that side of the atom has a partial negative charge. And since there's less electron density on the other side, we're showing that in red with a partial positive charge. That now, like I said, those electrons are repelling the electrons in the neighboring helium. And so that also sets up a polarization in the other atom. And so that's what the second view is. That's inducing a dipole. So now in this third picture, both atoms are polarized. And they both have temporary dipoles, which means that their electron density is temporarily unevenly distributed. And since they're both like that, since we've got now a case where I've got one atom, and I'm going to draw it a slightly different way than the picture is drawn up above. One atom, the electron density we can think of looks like this, where there's more electron density over here. So this is my partial negative, that's my partial positive. And that's going to attract to the other induced dipole, where this end is the partial positive. There's more electrons over here, that's the partial negative. This is my dispersion force. And that's just an electrostatic attraction between temporary dipoles. So let's look at some details about dispersion forces. And the first one has to do with when dispersion forces are stronger. And so let's first look at the size of atoms. So what I've shown here in the figure is the relative size of the halogen atoms, fluorine, chlorine, bromine, and iodine. And as you go down the column of the halogen, the size gets bigger and bigger. So those larger atoms, like iodine and bromine, as it's got the electrons further away from the nucleus, it's easier to polarize those electrons, or it's easier to induce a dipole in them, so that we say that they're more polarizable. If they're more polarizable and it's easier to induce a dipole, the dispersion forces are stronger in larger atoms. And one result of this is the differences in boiling point of these halogens. So now this would be for the diatomic molecule. The boiling point of the fluoride is negative 188 degrees C. The chlorine, is negative 32 degrees C. And both of those are gases at room temperature because they have pretty low boiling points. But you can see that the chlorine's boiling point is larger than the fluorine. And then bromine, we're finally up in the positive temperatures. It's 58.5 degrees C. So it exists as a liquid at room temperature. And lastly, the iodine is so big, its dispersion forces are so strong, its boiling point is a positive 184 degrees C, and it's a solid at room temperature. So again, the bigger your atoms are, the more polarizable they are, and so the stronger the dispersion forces. And so that not only goes for size of atoms, but as your molar mass gets bigger, also the trend is the same. So to expand on the idea of larger masses having stronger dispersion forces, I specifically want to look at alkane molecules or hydrocarbons and look at how the length of the carbon chain changes the IMFs. So let's do this a little bit in a different order. Instead of me talking about the IMFs, I'm going to give you the property first. So the boiling point of these substances is going to change according to the length of the hydrocarbon chain. And you can see that this table already lists what phase the compounds are found in. So now I'll give you the boiling points to back those up. For methane, the boiling point is negative 164 degrees C. Ethane, negative 89 degrees C. Propane, negative 42 degrees C. Butane, negative 0.5 degrees C. So those are all gases at room temperature. Finally, with pentane, we get up into the positive temperatures, and its boiling point is 36 degrees C, and hexane is 69 degrees C. So both of those are liquids at room temperature. So we can see that it gets harder and harder to boil the liquids as the chain length, so it stands to reason that we can conclude that the longer the hydrocarbon chain, the stronger the dispersion forces. So I've got some bad spelling in there. That should be larger, the dispersion forces. And I've got dispersion spelled a little bit wrong. That's okay. Okay, so again, the longer our chain gets, the stronger the dispersion forces. And this is just because of how much surface area there is. So for a chain, that's longer, and that's quite a bit longer than 6, when you think about two of those molecules interacting with each other, there's a lot of points of contact between them. Okay, so there's lots of surface area. So there's lots of points of contact, or lots of places that they interact. And so there's just stronger dispersion forces. And you can also just think about that in a mass perspective. So the longer the chain, you have a higher mass, which is just going to correspond to a higher boiling point. But it's all based on the dispersion forces getting stronger as your molecules get bigger. So the last detail here about dispersion forces goes back to the idea of surface area. And now it's not just about the length of the hydrocarbon chain, but it's about the structure, about whether it's branched or not. So this is a straight chain. And I put that in quotes because it's not really straight. Remember, the carbons are all tetrahedrally bonded to each other, but they're all bonded in one long chain. So this is pentane with the 5 carbons all bonded to each other in a chain. Then this next molecule, I've taken one of those carbons and I've put it on an interior carbon. So this is actually a butane. This is an isomer of pentane. Specifically, it's 2-methylbutane. This last molecule is also an isomer of pentane. It's 2,2-dimethylpropane. So it still has the 5 carbons, but now I've got 2 branches off the main chain. So these 2 molecules, like I said, they're branched. And when you have branched hydrocarbons, there's smaller surface area. So there's weaker dispersion forces. And we can see the result of this in the differences in boiling points. See from the boiling points that as the molecule gets more branched and gets a smaller and smaller surface area, the boiling point gets smaller and smaller, which means that it's easier to boil it, which corresponds to weaker dispersion forces. So the next type of intermolecular force I want to talk about is dipole forces. And these forces result from the electrostatic attraction between polar molecules, which are molecules that have permanent dipoles. So instead of having to induce a dipole, as we do in a nonpolar molecule, something like HCl with 2 different atoms with different electronegativities end up with permanent dipoles. So in this case, the chlorine atoms in both of the bonds are pulling on the electron density more strongly. So the electron density is towards that end of the molecule. So over here I have greater electron density, which I'm showing with the partial negative charge. And so that partially negative end of that molecule is going to attract the partially positive end of the other molecule. And that's a dipole-dipole force, or just a dipole force. Now these actually follow a trend that's kind of opposite to the dispersion forces, because these forces are going to be stronger when our dipole moments are stronger or larger, and that's going to occur when the electronegativity difference between the 2 atoms that are bonded together are larger. And in this case, the fluorine is a smaller atom. It's also more electronegative. So that bond is more polar. So the dipole is stronger. So the IMFs would be stronger in the CF than in the CO. And that also is a function of the fact that the fluorine can get in closer to the neighboring carbons on the neighboring molecules, and that again makes the dipole forces stronger. But that only holds when the molecules have similar molar masses. If the molar masses are significantly different, then the mass starts to have a bigger effect, and the corresponding dispersion forces can dominate the interaction that you're looking at. These 3 molecules that I've shown here sort of illustrate these differences or this trend. So the CH4 is completely nonpolar, and so it's just got dispersion forces. So it's got a very low boiling point of -161.5 based on the fact that it's just got weak dispersion forces. Then the CH3F has the same structure as the methane, but now it's got a dipole. So it is polar, and so there is a permanent dipole, and it's got a slightly higher boiling point because of the presence of dipole forces. And as we get bigger molar mass, both the dispersion forces and the dipole forces take a part in why the boiling point is even higher. The last type of intermolecular force I want to talk about is hydrogen bonding. This results when you have a hydrogen in your molecule bonded to nitrogen, oxygen, or fluorine. And what's special about the nitrogen, oxygen, or fluorine is those are the most electronegative elements. So as you can see in water, that sets up a dipole in the molecule, where here this is showing how my oxygen is partially negative, my hydrogen end is partially positive. That's a really strong dipole because the hydrogen is so small and because the oxygen is so electronegative. So when you have that and you have a collection of molecules that have a hydrogen bonded to a very electronegative element, you get hydrogen bonding because now you get an electrostatic attraction shown by the dotted lines between the hydrogen that's bonded to oxygen in this case, interacting with the very electronegative oxygen on a neighboring atom. And this is a really strong IMF. It's stronger than typical dipole forces. Data here to illustrate the strength of hydrogen bonding and how that changes boiling points in similar molecules. So we've got H2O, which is very similar, exactly identical in structure, in fact, to H2S. Sulfur is actually below oxygen, so they're going to bond in the same way. But water is a liquid at room temperature with a really high boiling point of 100 degrees C, whereas H2S is a gas at room temperature with a boiling point of negative 60 degrees C. And that's due to the strong hydrogen bonds in the water as compared to the dipole forces in the H2S. And then ammonia and the corresponding molecule that would be formed by the atom under nitrogen, phosphorus, shows the same kind of trend. They're both gases at room temperature, but the ammonia has a much higher boiling point at negative 33 because of its hydrogen bonding compared to the PH3, which has a boiling point of 88 degrees C. Table kind of sums up everything we've talked about with regard to dispersion forces, dipole forces, and hydrogen bonding, or in other words, IMFs. Okay, so this bottom row of data, these are group 4 elements bonded to hydrogen. They're all nonpolar. And as you go from carbon down that row to silicon, down the row further to germanium, and then down to tin, your mass is increasing. So this would be my column. I've got carbon, silicon, germanium, and tin. So as I go down that column, that's increasing mass. And we can see that the IMFs are going to increase in that direction also, because with dispersion forces, the greater the mass, the greater the dispersion forces. And that's shown by going in this direction, we have a larger boiling point. And in fact, that's the trend that we see for all of these things as they're bonded to hydrogen. That works for the group 3, the phosphorus, arsenic, and antimony. The group 6, which is chlorine, bromine, and iodine, and the group that was group 7, and the group 6, sulfur, selenium, and tellurium. As those masses increase, dispersion forces increase, and the boiling point increases. So again, this is mass increasing, dispersion force increasing, and boiling point increasing. And then this last member of each of those groups, so oxygen, fluorine, nitrogen compared to carbon, those are getting more and more electronegative. So you would expect actually that the HF should have the highest boiling point because that's the most polar of the three. But what's going on here is hydrogen bonding. And in the case, the water has the highest boiling point because of its hydrogen bonding with the oxygen, then HF, then NH3, then CH4. And those increase not really necessarily in the direction we would expect them to based on position on the periodic table, but it comes down to also the structure of those substances that gives them the different boiling points. How do we go about determining what IMFs a substance has? And the answer is you follow this flow chart. And basically what you have to decide is my molecule polar or not? And so if my molecule is completely nonpolar, then I'm just going to have London dispersion forces. Those can also be called van der Waals forces. And then those are going to vary with increasing molar mass. They'll get stronger and stronger. If your molecule is polar, then you have two choices. If the molecule has hydrogen bonded to nitrogen, oxygen, or fluorine, then you have hydrogen bonding. If the molecule doesn't have hydrogen bonded to oxygen, nitrogen, or fluorine, you just have dipole forces. And really, these are kind of listed in increasing order of strength. If your molar mass is all the same, so if your molar masses are similar, the strength of IMFs go as dispersion forces are less than dipole forces, which are less than H bonding. So thank you for watching and see you again soon.